Hello everyone, my name is Atish and topic of this learning video is Diagonalize the matrix by orthogonal transformation. So without wasting time, let us see the definition of orthogonal matrix. Orthogonal matrix is very important when you are learning the topic Diagonalize the matrix by orthogonal transformation. So let us see the definition of orthogonal matrix. Suppose you have a matrix say A, okay? Then take the transpose of this matrix. So AT and AT denotes the transpose of this matrix. If the multiplication of this gives you an identity matrix, then we say that matrix A is an orthogonal matrix. Another definition of orthogonal matrix is orthogonal matrix consisting of the orthogonal unit vectors. Okay. So a matrix consisting of orthogonal unit vectors is known as orthogonal matrix. Okay. Now sometimes orthogonal matrix is also defined as the matrix whose rows and columns are orthonormal vectors. Okay. So these are the three different definitions. Okay. If you want, I can write one definition. It is. Let me use this. Matrix A, and matrix should be square, okay? So to be precise, a square matrix A is said to be orthogonal if A into A transpose is equal to I, or some people use the transpose as A into A dash is equal to I, where what is I? I is an identity matrix, where I is an identity, or you can write unit matrix. Okay. Now let us take an example of it. So for example, I am taking, let matrix A is equal to, what is it? Matrix A is equal to 1 by root 2, 1 by root 2, 1 by root 2 and 1 by root 2, and say this is to be minus. Now this matrix is a diagonal matrix. If you want to see whether this matrix is diagonal or not, you can actually verify. For example, this A is equal to this, there A into A dash is equal to, what is it? Matrix I have 1 by root 2, 1 by root 2, minus 1 by root 2 and 1 by root 2. This is the matrix. Now take the transpose of this matrix, that is A dash. So what is it? 1 by root 2, 1 by root 2, minus 1 by root 2 and 1 by root 2. Okay, so this is the matrix. Now just multiply it. So the moment you multiply, what is it? 1 by root 2, 1 by root 2, that is 1 by 2. 1 by root 2, 1 by root 2 plus 1 by 2. And what is it then? First row, first column, first row, second column. 1 by root 2 into 1 by root 2, that is minus 1 by 2, and this is plus 1 by 2. Likewise, you can solve this row, this column. So this will gives you minus 1 by 2 plus 1 by 2, and the last one minus minus plus 1 by 2, and this is 1 by root 2 into 1 by root 2, 1 by 2. Okay, half plus half is 1, so I can write it here only 1. Minus plus gives you 0. This also gives you 0, and this will gives you 1. Okay. So as you can see, A transpose is equal to identity or unit matrix. So what we can say? We can say that this matrix is nothing but an orthogonal matrix. Okay. Now I would like you to pause the video for a minute or for a few seconds and come up with the simplest example of orthogonal matrix. So just pause down the video for a few seconds. So I hope you might have come up with the example. Simplest example of orthogonal matrix is identity matrix, is it? You just see it is to be 1 0 0 1. Okay, identity matrix. Then what is its transpose? 1 0 0 1. What is its multiplication? Identity into identity is identity. Simple. Okay, now let us take the working rule of this. So working rule, let me write down the working rule. So the working rule comprises of 6 steps. Step number 1, steps. So the first step is find eigen values. So that is your first step. Second, find eigen vectors. This is your second step. Find out eigenvalues, eigenvectors, and then the third step is write orthonormalized eigenvectors. I will tell you how to find out the orthonormalized eigenvector. And the fourth one is write orthogonal, or first of all, yes, write orthogonal matrix. After finding out the orthogonal matrix, you just need to find out its inverse. Find inverse of an orthogonal matrix. Okay, and we'll denote this orthogonal matrix in this topic as Q. Okay, and the last thing is find out the diagonal form. Find out the diagonal form using orthogonal transformation. The transformation is Q transpose A Q, where what is Q? Q is an orthogonal matrix. Okay, now the first two things you can easily find out. I will let you know how to find out the normalized eigenvectors. Okay, suppose you have eigenvectors, say x is equal to 1 1, and if you wish to find out the orthonormalized eigenvector, so what would be the orthogonalized eigenvector? So it should be, you just write 1 upon under root of 1 square plus 1 square. This element upon the length of this vector. So what is the length of this vector? Under root of this square plus this square. And what about this? This is also 1 upon under root 1 square plus 1 square. So what is orthonormalized eigenvector? 1 by root 2, 1 by root 2. Okay. If there are 3 elements in the eigenvector, you can easily find out the orthonormalized eigenvector. Okay. Now this is about the orthonormal. Next thing is orthogonal matrix. Once you orthonormalize the vectors, just place in the matrix, you'll get orthogonal. Now you have to find out the inverse of orthogonal matrix. Suppose you have a matrix, say Q, and matrix Q is orthogonal. So because matrix Q is orthogonal, so by definition Q transpose is equal to I. Okay. Now you can multiply by Q inverse on both sides, or you can take this orthogonal matrix to the left. So what you'll be getting? Q transpose is equal to Q inverse. If you are not happy with this, just multiply by Q inverse on both sides. So this Q inverse become identity. Identity into anything is anything, and then identity into anything is anything. So finding inverse is not a big deal. You just have to, once you get the orthogonal matrix, you just need to take the transpose to get the inverse. Okay, and then at last you have to find out the diagonal form using the orthogonal transformation. This transformation you can also write it as Q is an orthogonal matrix and Q transpose is same as Q inverse, so you can write it as Q inverse AQ. Okay, you can make use of anything. Okay, so let us take an example to work out, and you have to remember these working rule in order to get the solution of the problem based on this topic. So let me write down the problem. So a simple problem I will be taking in order to make the understanding more clear. Okay. So example is diagonalize the matrix A is equal to 1 1 1 1 by orthogonal transformation. Okay, so we have a matrix and we have to diagonalize this matrix. So let us find out one by one. So what is the first step? The first step is find out the eigenvalues. So you can write let A is equal to matrix 1 1 1 1. This is the matrix and we have to find out the eigenvalues. So you can write eigenvalues are given by, so eigenvalues are given by what? Determinant of A minus lambda I equal to 0. Now you may be wondering, I am writing A minus lambda I. Only for the Sylvester's theorem we have written lambda I minus A. Okay, so find out what is it. This is 1 minus lambda, then this is 1 1 1 minus lambda is equal to 0. Because the matrix is of 2 by 2, so we'll be having a quadratic equation lambda square minus s1 lambda plus determinant of A lambda square. Now you are smart enough to get the values of s1 and determine what is s1. S1 is trace. What is trace? Sum of the diagonal elements. So what is sum of the diagonal element? 1 plus 1. So minus 2 lambda. Plus what is the determinant? 1 into 1 minus 2. So 0. Simple. Now you can easily solve. So you can solve this as lambda square minus 2 lambda equal to 0. That is, you can take lambda common. Lambda into lambda minus 2 equal to 0. Therefore, lambda equal to 0 and lambda minus 2 equal to 0 means lambda is equal to 2. So we have two different eigenvalues, 0 and 2. Okay. So for these eigenvalues, we have to find out the eigenvectors. Okay. You may be wondering, or if you remember exactly, we have already done such kind of thing in the topic of characteristic equation, eigenvalues and eigenvectors. Okay. So let us write down one sentence. Let x1 x2 transpose be the eigenvector corresponding to an eigenvalue lambda such that what is it? Such that A minus lambda I operating on x is equal to 0, and I can certainly say let x is equal to this. Okay, now you have a matrix, you have a vector x1 x2, so let us find out. So what is A minus lambda x? 1 minus lambda, 1, 1, 1 minus lambda. What is x? X is x1, x2 transpose. So I can write it as a column matrix. x1, x2 is equal to 0 can be written as 0, 0. Now just find out, you can find out this one as 1 minus lambda, first row, first column into x1 plus x2 equal to 0. Okay. Now do the similar kind of multiplication and get the second equation. So this is x1, 1 into x1, x1 plus 1 minus lambda into x2 is equal to 0. Okay. Now we have, say this is to be equation number, say this is to be set of equation A. Okay. Now we'll find out the eigenvector using this equation. So let us take first of all lambda equal to 0. For eigenvalue lambda equal to 0, equation A will imply, what is it? Lambda equal to 0. So this is x1 plus x2 equal to 0, and this also gives you the same, x1 plus x2 equal to 0. Simple. Now both the equations are same, so both the equations will imply x1 is equal to minus of x2. I can write this one as x1 upon 1 is equal to x2 upon minus 1. Simple. So for lambda equal to 0, we got the first eigenvector. So you can write here, it is a good practice to write systematically. For lambda equal to 0, eigenvector is equal to, what is it? 1 and minus 1. Very simple. Okay. Now likewise you can find out for lambda is equal to 2, what is the eigenvector. So let me rub this. So I will write for lambda is equal to 2, equation A will imply, equation A is this. Okay. Now put lambda is equal to 2. So what is it? Minus x1 plus x2 equal to 0, and here x1 minus x2 is equal to 0. So both this equation will imply x1 is equal to x2. That is what we can write, x1 upon 1 is equal to x2 upon 1. So you can add one sentence here like this. For lambda is equal to 2, we have the second eigenvector x2 as 1, 1. Okay. So we have this eigenvector. Now we have eigenvector x1 and x2. Now this completes step number 2. Now step number 3 says, what is it? Write down the normalized eigenvector. So let me write, therefore normalized eigenvectors are, so how you can normalize this vector? You can write down the same vector and x1, and you can write it as 1 divided by under root of, for this I can write down 1 upon under root of 1 square plus minus 1 square. Okay. Try to write like this, because what happens, sometimes you write 1 square minus 1 square. So sometimes you write like 1 minus 1 0, which is not the case. Okay. It becomes undefined, not defined. Okay. So what is the eigenvector for lambda equal to 0? Yes. What is it? 1 upon under root of 1 plus minus 1 square. So this is root 2. And what about for this? For this, minus 1 upon root 2. So we got the eigenvector. This is the first one. And what about the eigenvector for this? Eigenvector for this is 1 upon under root of 1 square plus 1 square. So what is it? 1 by root 2, and this is also 1 by root 2. Okay. So to find out the normalized eigenvector, what you need to do is write down the element, divide by the length of the vector, precisely eigenvector. Okay, so we have now normalized eigenvector. So let us write down the orthogonal matrix, and as you know that we are going to denote the orthogonal matrix by Q. Therefore, orthogonal matrix, orthogonal matrix Q is equal to, what is it? Orthogonal matrix, write down this first and then second column. So this is 1 by root 2 minus 1 by root 2, then 1 by root 2 and 1 by root 2. Okay, so this is nothing but the orthogonal matrix Q. Now what you need to find out? Find out the Q inverse or just the Q transpose. Okay, therefore Q inverse is equal to Q transpose. Why Q inverse is equal to Q transpose? We have already seen in the beginning of the lecture. For the orthogonal matrix, Q inverse is equal to Q transpose, which is equal to, very easy now, first row become first column and second row become second column. So 1 by root 2, 1 by root 2 minus 1 by root 2 and 1 by root 2. So we got the inverse of this matrix. Now what we need to do? We just need to find out the orthogonal or the diagonal form using the transformation, using the orthogonal transformation. What is it? Q transpose AQ. So let me write, therefore Q inverse AQ, you can write Q inverse AQ or you can write Q transpose AQ, one and the same thing, is equal to, what is Q inverse of Q transpose? This is orthogonal transformation, huh? So this is 1 by root 2 Q inverse, okay, 1 by root 2 minus 1 by root 2 and this is 1 by root 2. Do you remember what was our matrix A? Matrix A is 1, 1, 1, 1. Okay, and what about Q? We have Q, this matrix, orthogonal matrix, 1 by root 2 minus 1 upon root 2, then 1 by root 2 and 1 upon root 2. Okay, so we have the matrix. Now solve this. If you are getting the diagonal matrix consisting of eigenvalues, means whatever you have done is absolutely correct. Okay, so just multiply this. So I am writing the first matrix as it is, 1 by root 2, 1 by root 2, then 1 by root 2 with minus sign, 1 by root 2 into. Now multiply this matrix with this. Now see here, this is 1 by root 2 minus 1 by root 2, 0, 1 by root 2, 1 by root 2, 1 by 2, is it? Now 1 by root 2 minus 1 by root 2, 0, and what about this? What about this? First row. Okay, Q inverse AQ, okay. Then it is 1 by root 2, 1 by root 2. So 1 by root 2 plus 1 by root 2. It is 2 by root 2, sorry. Let me solve it once again. 1 into 1, 1 by root 2 minus 1 by root 2, 0. Then 1 by root 2, 1 by root 2. So this is 2 by, no, not 1 by root 2 into 1 by root 2. So this comes out to be 1 by 2, correct. But it is, we have to make it plus. It's 2 by root 2. Next is 1 by root 2 and 1 by root 2, 0. 1 by root 2 plus 1 by root 2 is 2 by root 2. Okay, now multiply this. So the moment you multiply this, first row, first column gives you 0, 0 into 0 plus. Then this, what is this? 1, this is 2 by 2 minus 2 by 2. This gives you 0. I am having a habit of doing some rough work, okay, to make sure whether we are doing correct or not. Now this into this plus this into this, 0. Now see here, this is 2, by 2, and this is also 2 by 2. So this is 1 plus 1, which is 2. So as you can see, at last what you got? We just get the diagonal form. Okay, so this is my Q inverse AQ, and this is nothing but my required diagonal form. Okay, so just we have seen, if you are given a matrix, and then how to diagonalize that matrix using the orthogonal transformation. So I hope this is making sense, and thank you for watching this learning video. If you have any queries, just contact me. Thank you.